What's going on, everybody? This is Mr. Diamond, and my PowerPoint little dot is very good at hiding on this PowerPoint screen. I didn't even realize. We're going to be doing our section notes over identifying forces. This is going to be a quick run through. I'm probably not going to actually really work out the example problems related to it until next week. We're going to focus more on just identifying the actual forces and being able to understand them this week. So we're going to go through most of the forces that will be relevant for this chapter. The first and easiest force to identify in your problems is going to be gravitational force. As you probably noticed if you watched the free body diagrams video already, gravitational force is what normies call weight, and it's always being exerted if you're on or in the gravitational pull of any planet, asteroid, anything like that where there's a gravity pulling you down. Unless otherwise stated, it's always directed straight downwards, even if an object is on a slope, and it has on Earth at least an acceleration of 9.8 meters per second squared. Up until this point, we were ignoring gravity unless something was in the air, but keep in mind that it's actually what's holding things on the ground as well. It's preventing things that they're not floating away from floating away. So since we don't have an acceleration if you're standing at rest on the ground, there must be another force at play that keeps you in place. And if you've watched the force video or the free body diagram video, you already know what I'm talking about. If not, you'll recognize this a little bit from Newton's third law. But we call this force the normal force. This is the force that acts as an opposite force of gravity in most cases. It's a supporting object or supporting force. So for example, while I am, well, I guess I'll just use me sitting. So I'm sitting in this chair right now. Gravity is attracting my weight towards the gravitational center of the Earth, and it's pulling me downwards. But I'm not just falling through the chair, ideally. Hopefully that doesn't happen by the end of this video. Instead, the chair is supporting me, and it's pushing back upwards on me, keeping me in place. The force that is the equal and opposite force coming from the object that I am exerting my weight upon is the normal force. It's the supporting force. It's directed perpendicular from the surface the object is resting on. So since my butt is going like downwards and it's on a surface that is flat, it's directed upwards. If that surface was angled, it would be at a 90-degree angle from there, which I now just realized after I've gone out of order that I mentioned that as though you already knew it in the free body diagram video. So I don't know what order you'll watch these in. It's really kind of up to you. Both of them are relevant. I just didn't want to do them all in one video. It is also, it doesn't have to necessarily be straight upwards though. Make sure you keep that piece in mind. It's perpendicular. So that also means if you're like pushing against the wall, like if I turn around and don't destroy things, and I push against this wall, the normal force is actually pushing outwards because it's preventing me from going into the wall or falling through the wall. There's some example problems that I'll work out, but I'll probably work these out next week just because we're going to focus more on actually identifying the forces, and I don't know how much time I'm going to have to actually work these out, just to be honest. Okay, now what if we pulled upwards? That's the example problem. Okay, so what if you are pushing an object that is at rest? So we're no longer talking about something that's vertical or like going up and down. There's no gravity in this case, or there is gravity, and there's not really any sort of like normal force that we're really concerned with. But what if you're trying to push something? Normal force and gravity are going to be relevant to that. But there's no guarantee that an object is going to move. I can push on this desk with a small amount of force and it's not going to move. And that's because there must be something counteracting that push. Now we know there's inertia, and that inertia is the likelihood or the tendency of something to stay in place. But it's not just the tendency of something to keep it at rest. There's actually something preventing it from moving and making it harder to get it moving. And that force is something that we discussed a little bit before. It's called friction. Friction is the resistance of motion of one object relative to another object. In this case, it's the ability for this desk to resist moving across the tile floors here at the school. It could also be the resistance of my phone moving across my hand, this pen moving across this paper. All of those are examples of friction. It's how hard is it for object A to move across object B. Frictional force is actually related to the normal force, which might make sense if you've ever had to do any like furniture moving. Heavier objects are harder to move, but one of the ways you can usually alleviate that is by lifting up slightly. Like don't just drag, lift. Usually means that you can actually get it to slide off of the surface. Even if you're not actually physically picking it up off the ground, you should have an easier time sliding something over carpet or rough surfaces if you can lift it upwards just a little bit, even if you're not physically moving it upwards. Adding that upwards lift helps reduce the normal force, and that actually means it's going to reduce the frictional force. So the way that we actually relate them together is based on a mathematical coefficient. We call that the coefficient of friction. It's represented by this little backwards or upside down h, or as the Greek letter is called, it's a mu. There are two kinds of friction coefficients. There's kinetic friction and then there's static friction. Kinetic involves motion. So when something is moving, it is experiencing kinetic friction as it's moved along. So like if you push a box on a carpeted floor as it's moving, friction is making it harder for that thing to move, and it's requiring you to continue pushing. And when you keep shoving it, you have to keep overcoming that that kinetic friction force. If the object is at rest, it is going to be experiencing static friction if you are pushing on it. Objects don't just experience static friction while they're at rest. Like this bottle in my hand is not experiencing, well, it's not experiencing a lot of forces because it's falling. But my phone in my hand is not experiencing static friction. Only as you begin to apply force and it's not moving is the friction of my hand starting to react against it, preventing it from moving. And if you keep pushing harder and harder and harder, eventually you should overcome that force of static friction and you'll get something moving. And when you do, you've now switched from static friction to kinetic friction. So me pushing on my desk without it moving, well, I moved it a little, but pushing on my desk without it moving, that is static friction preventing it from going. But once I start the desk moving, kinetic friction takes over. This is actually also why you may have realized in your day-to-day life that usually getting something moving is a lot harder than keeping it moving. If you've ever had to like push a car because someone's car broke down, getting it to start moving is the most important piece. Once it's moving, it actually usually doesn't take nearly as much force to keep the thing moving. It's also something that any weightlifters or people who do any sort of especially deadlifts and stuff like that. When you do a deadlift, you're supposed to start from a dead stop. It's part of why it's called a deadlift. And that's because you are making it harder because you have to overcome that static force. You have to overcome everything at once. You don't get an advantage from something and just moving as it's already going. When you're lifting weights and things like that, you don't want to, if you want to get the maximum amount of force, you don't kind of use the movement of you falling to kind of overcome it. It's a lot harder if you go from dead stop, lift, dead stop, lift. I don't know if any of you lift weights to have realized what I'm talking about there. I don't feel like there's as huge of a cross section as there might be in some of my other classes about that. But if there's at least one of you, I'm sure you know what I'm talking about with the whole, it's harder to start from rest than it is to start while moving. So here's just a list of a bunch of different static frictions and kinetic frictions. Wood on wood has a static friction of 0.4 and a kinetic friction of 0.2. So again, you notice a common theme as you just glance down here. All of the kinetic frictions are smaller than the static frictions. Static friction, again, it's a lot harder to start something moving because you have to overcome a lot more inertia than it is to keep it moving. Because once it's moving, inertia wants the thing to keep moving, so you don't have to fight as much. Basically, when you start getting something moving, you're working against inertia. When you're keeping something moving, you're working with inertia. You're on the same side as inertia, so it makes the job a little bit easier. We can actually get these things pretty low. Things like lubricated ball bearings, which are like those completely smooth metal balls lubricated in a specific joint or a piece of machinery, they can have it less than 0.01 coefficient of static friction, but it's basically impossible for us to have zero friction on this planet. We haven't found anything that is considered a frictionless surface. Now, we can use the coefficient of static friction to actually figure out how much force you need to move an object. Because again, static friction increases. The more you push on an object, the harder static friction is going to push back on you until you hit the maximum amount of force that it takes to move an object. And so you'll figure out that if you apply a force greater than the force of static friction, the maximum of it, you will get an object to move. And in this case, we've got our mu of static friction. So if we go back here, and let's say we're going to go with ice on ice. That's 0.1. And then we're going to say that our normal force, our thing had a normal force of 100 newtons. 100 newtons times our 0.1 back here means that a force of 10 newtons is required to get an object moving. If you apply 1 Newton of force, 1 Newton of static friction will push back on you. If you apply 5 newtons of force, 5 newtons of static friction will push back on you. If you push 11 newtons of static or of force on it, it will begin moving, and you will now flip to the ice on ice's kinetic friction because you've gotten that object moving, and you'll then start caring about that 0.03 number instead of the 0.1 number. It'll make more sense when we do some problems with this, but we're not going to focus on those problems until mostly next week. This is just kind of giving you an idea of how this force works. Okay, that's what I've got as far as forces. Again, the 3 key ideas are the 3 key forces we're going to focus on here: gravitational force, normal force, and friction. And then any other force you apply will also be in problems: pushing, pulling, dragging, yeeting, yanking, anything like that. I'll go into more detail about this frictional force stuff again next week. Don't freak out if you feel like I rushed through it a little bit. I'm also a little bit out of it because I've recorded so many videos today, so mea culpa. It's a little bit weird here at the end. If you have any questions, please shoot me an email. This should give you enough of a head start. You can start working on the worksheet. In the meantime, though, this is Mr. Diamond signing off. Hope you have a good rest of your day, everybody. Hope to see you or hear from you soon.